no exam, right? So you don't need to understand this. This is just really because it's just interesting. Why, when you did on the simulator, you took one reactive component and one purely resistive component, did you have something that was frequency dependent? Why? Well, one of the things that you've got is with an inductor, and we haven't done inductors yet, but what we've got is, instead of using R, we use X. And what that means is that's reactiveness. It's equivalent AC resistance. We could write R, but it would be confusing, so we write X. So the equivalent DC resistance is 2 pi F L, and L is the value of the inductor. Now we can do the same for a capacitor. We can say, now we want the equivalent capacitive reactance, the equivalent resistance the capacitor has, but of course that's frequency dependent as well. And that is 1 upon 2 pi Fc. So now I've got two equations which, if you give me the frequency and the size of your capacitor, when we put it in a circuit like this, so there's my V in, there's my V out. If you give me my unknowns, I'm not too worried about the amplitude of V in because we know it's a sine wave, or that's what we've been using. So the amplitude doesn't matter too much. What I want to be able to do is I want to numerically say, well, I don't like these things, they're complicated. I want to replace this with a resistor. Well, I've got it. Oh. There's an equation that replaces this horrible thing with this. Well, it's still horrible, but it's plausible, right? Everything in there is knowable. So you give me the frequency, I can tell you the impedance of that capacitor at that frequency. That's clever, that's clever. Now I know that from the potential divider, and I can derive this equation for you, I've actually done it already for a potential divider on the 721 web pages and the videos there. If you go down there, there's some, well, there's loads of tutorials, but this is one of them. If that were a standard potential divider, like this, V out is equal to V in R2 on R1 plus R2. I can derive that, like I say, I've already done it, have a look at the videos, but most people just remember that because it's legacy, it's just really, really fundamental. So if now with a leap of faith I said, well, this is R1, and I lied to myself and I said this is R2, what I could do is every time I see R2 in this equation, I could replace it with this. Get a bit messy, right? Now, there's a very clever man called Laplace, and really all he's done is made this observation that said, well, actually it's a bit more difficult than this because it's not just amplitude, it's phase as well, so therefore it needs to go into the complex plane. But let's forget all about the complex plane altogether for the time being. Let's just say, what we could do is we could just say that 2 pi f is omega. We just say it's omega. So this whole part here is just the angular frequency now rather than the frequency. Now someone jumped ahead there and they said, well, let's replace it with S. Why not replace it with S? We can replace it with S, T, U, V, W, X, Y, Z. Let's use a symbol in there and let's say, for the sake of argument, that this capacitor we can actually represent as 1 upon SC. So under these circumstances, what this means is S is actually 2 pi F. it has to be complex, but forget the complex part for the moment. So now, you start to see a bit of magic, because under those assumptions, if I take this equation here, and every time I see R2, I replace it with 1 upon SC, the same argument is true for this one for the inductor, where every time I see an inductor, I replace it with SL. But now if I do this for the capacitor, because you've got this circuit here, if I say that, so this is impedance, okay? It's really important to note. 1 upon SC is an impedance, a complex impedance. This is a complex impedance, resistance basically. So what I can do is I can say, well, R2 upon R1 plus R2. Forget V in, because we know we're going to wire it up to V in, it's immaterial. Every time I see R2, I replace it with S, 1 upon SC. So I get 1 upon SC upon R1 plus 1 upon SC. Bit messy, right? Simple algebra, multiply top and bottom by SC, I end up with 1 upon SCR plus 1. So what? What does that tell me? What does that tell me? Tell me. Second?
Is it the transfer function of like...
It's the transfer function, yeah. I'm sure it's the transfer function. But what does it tell me? It tells me lots of things, because it tells me as S tends towards 0, so I make S lower and lower. Remember, S is, we're saying it's
angular frequency.
the angular frequency, but it's complex, but forget the complex. So we're saying as the frequency heads towards 0, well, what happens to the equation? We end up with this part here equals 0, and it's 1 upon 1, so the output goes to 1. Well, that's what we know with this circuit, isn't it? At low frequency, the output is what we put in. Let's see what happens if S goes towards an infinitely large number. What do we end up there? Well, an infinitely large number plus 1 is just an infinitely large number. We end up with 1 on infinity. Output changes to 0. And no magic. Just from the maths. So the maths has just reinforced exactly what we believed to be the case before. Now we can do a similar thing for the capacitor and the resistor around the other way. We can do similar things for capacitors and inductors altogether and everything. But it's just where that type of stuff comes from. Now remember that S is complex. So there's actually quite an interesting point. If we look at the denominator, we've got SCR plus 1. Imagine a situation where we could make the denominator 0. We'd have 1 upon 0, which would be infinity, right? Well, we can, because we can say that SCR must therefore equal minus 1, because minus 1 plus 1 is obviously 0. So what that means is that where S is equal to minus 1 upon CR, or if we now turn S back into 2 pi F, F is equal to 1 upon, forget the negative because that's just because it's complex. We've got 2 pi CR. That gives us the frequency of where it starts to drop off. All from the maths. All from the magic. So maths is good, not bad. It's there to help you, not confuse you. Okay, so there's a nice little analysis there. I can do the same for you in a minute if you want, for the capacitor and the resistor around the other way on the high pass filter, but there it is. Didn't understand it first time round? It's on the video, I'll upload it to 721 webpage. Okay?
Okay.
Thank you.